This is section 7.4, graphing rational functions. And on page 491, Algebra 2. So, it's another name for rational.
Fraction.
That is correct. We're going to graph rational functions. So in other words, we're going to graph functions that have, they're in fraction form, but is in the form, and this book uses, because every Algebra 2 book uses something different. But this is a rational function, where we have a numerator and a denominator, and they're both functions. Okay? Now, since it has a denominator, we have some values that don't work. And once again, we have to introduce that concept of an asymptote. Now, we're going to have vertical asymptotes and we're going to have horizontal asymptotes. And we're not going to be just defined by an x squared term. They're going to go much larger. Okay? So they give us a little bit of help on page 491 on how to graph. Okay? There's two things that we need to be concerned about. Asymptotes and zeros. Now, you remember that an asymptote is a line that we get close to but we never cross. Okay? A zero is where the function touches the x-axis. Now, I don't know if you remember this or not, but zeros are also called solutions or roots because they satisfy the equation. They make the equation zero. So where it touches the x-axis means that y equals 0, right? We don't go up or down. Make sense? Okay. So we need to be concerned with these two things. The zero is fairly easy, all right? The zero, going back to this, the zero is where a sub x equals 0. So if you solve the numerator, if you say the numerator, where is the numerator 0, that will give you the zeros.
Is that negative a or?
No, it's
just a tick mark.
It's just a tick mark. Okay, I didn't know how to do it. Maybe an arrow, would that be better? Okay, I see what you're saying. A to x, a of x, it's hard to say. A of x is a function, Joey. It's a function, not a number. It's a function, okay? All right, so if you look at that chart in page 491, it says, if f of x equals a to the x over b of x, and a and x or b of x are polynomial functions with no common factors, that means you can't cancel, all right? That means these two don't have anything in common. They have something in common, you can cancel. They don't have anything in common. Here's how you get the asymptotes. The vertical, we're talking about this function here. The vertical asymptote is where b of x equals 0. So in other words, you set your denominator equal to 0, and that says denominator. You can't read it. Where the denominator is 0, that is where your vertical asymptotes. Your horizontal asymptotes, not so easy. Now remember, your vertical ones go up and down, right? Your horizontal goes left and right. We're going to now start really pushing you to make asymptotes vertical lines or horizontal lines that are dashed. So I want you to dash. And I didn't count it off in the quiz if it was solid, but from now on we want them dashed. Okay. So here we have it. If the degree of a of x, that's the numerator, and degree is the monomial exponent, the highest degree monomial. Remember degree? If you take the highest monomial, its exponent, that's what it is. Okay. if the degree of a of x is greater than the degree of b of x. Okay? There is no horizontal asymptote. Alright? There's no horizontal. Now, I'm going to tell you something. There's a slant. There's a possibility of a slant asymptote, which I'm going to get to in a little bit, but there's no horizontal. So, let's say if this has an x cubed term, and this has an x term as the highest degree, there's no horizontal asymptote. So you got to look at the degree. All right, the second one, oh, by the way, let's go ahead and let's do them all and then we'll take a look at pictures. If degree of a of x is less than the degree of b of x, there is asymptote at y equals 0. So in other words, the x-axis right here is the asymptote. Okay? And then finally, if the degree of a of x is equal to the degree of b of x, okay, then the line is, we have a line, this is a line, y equals the, do you remember LC was the leading coefficient, or do I need to write that out? The leading coefficient of a of x, the top, over the leading coefficient of b of x. I'll erase that and write it better. And I'll go through each one of these, so don't panic. If you're going, I have no idea what he's talking about. Okay. This book does an excellent job of giving examples of these. And one of the better books I've had. Now, it's not always the greatest at some things, but okay. Let's take a look at number 1 here. Let's call this A, B, and C. So you know what I'm talking about. Okay. Take a look on page 491. We're going to talk about A.
Bless you.
Thank you. I think I just spit on the board.
Here.
Did I? All right. Got that on tape too, so you can watch that later. Make sure you see it, you know.
Yeah.
All right.
Your
So,
back was turned to the camera. We won't
oh,
see it.
okay. We won't see it. So this is A. All right. F of x equals x squared over x plus 1. Man, my writing is stinking. Sorry. Okay, let's take a look at A. So it said the degree of A of x, which is 2, is greater than B of x. So there's no horizontal asymptote. So you take a look at that picture on A. You see that? Do you see there's no horizontal asymptote?
Mm-hmm.
Okay. All right, there is a vertical one, right?
Mm-hmm.
The vertical one comes from this. X equals a -1, right?
Mm-hmm.
All right. Okay, let's take a look at B. The situation B. The degree is less, the degree of the numerator is less than the denominator. Let's take a look at this one. F of x equals 3 over x squared minus 1. Okay, you'll see that the degree of x in the numerator is 0. The degree of the denominator is 2. So this is less than. So basically, we have 3 asymptotes. The first one is y equals 0. That's our horizontal asymptote, right? And then we also have x cannot equal 1, or excuse me, x equals 1 and x equals a -1, because you can factor this as x minus 1 times x plus 1. Do you see where the vertical asymptotes are coming from?
Yeah.
Okay. Now the vertical asymptote up here was x equals a negative 1, right? Okay. All right, does everybody see it? So take a look at the picture then. The second picture on page 491, we have two vertical asymptotes at 1 and an x equals 1 and an x equals negative 1. By the way, when you have that quiz, the asymptotes are x equals. They're lines, or y equals. And then we have one horizontal asymptote at the x-axis. Any questions? Yes.
On the first one,
Uh-huh.
on x squared, on that one,
This one here?
the
Yep.
top one,
Yep.
why is there not, like a y asymptote? Like,
Because this is larger than that. The exponent 2 is larger than 1. If the exponent, the highest degree in the numerator, is greater than the denominator, there is no horizontal asymptote.
okay,
But this one has a slant asymptote, which I didn't tell you about yet.
okay.
And it's complicated, okay? All right, and the last one,
Yeah.
see, these are kind of memorization, aren't they?
Yeah.
You know, you can kind of memorize these. The last one is, if the degree is equal, so we have something like this. 2x plus 1 over x minus 3. Okay. Josie, the exponent of this one is 1 and this one is 1. So what happens is, here, watch this very quickly. First of all, we have a vertical asymptote at x equals 3 because of this, right? Then we have a horizontal asymptote at y equals, now watch. The leading coefficient, which is 2, over the leading coefficient here, which is 1. This is the leading coefficient is 1. So I get y equals 2 if I simplify it. So I have a vertical asymptote at x equals 3 and a horizontal at y equals 2. All right?
This one's, yeah.
These are your 3. Okay, so what are you going to be doing? Well, you're going to be graphing something like this, correct? All right? So let's take a look at your assignment. Okay, this is number 13. Okay. F of x equals x over x plus 2. Okay, so it says graph each function. We're going to use these concepts to understand how to graph this rational function. All right? Well, let's take a look here at what happens. First of all, what is its vertical asymptote?
X equals
X
negative 2.
X equals a negative 2. So we have a vertical asymptote at x equals a negative 2. Josie, make sure that we can see this on the video.
If we can.
Okay? Now can you?
Yeah.
Can you see 13 too?
Yeah.
Okay. Okay, so we have x equals a negative 2 as our vertical asymptote. You understand? So it's going to be somewhere around here, all right?
Yeah.
Okay, now you'll notice that the degree of the first numerator is 1. And the degree of the leading coefficient of the denominator is 1. So they're equal, which gives us this third option, which says if they're equal, then you have a y-intercept, or excuse me, a y-asymptote of 1 over 1, which is 1. So we now have a horizontal asymptote at this. Okay, now that we have those, I'm guessing, since it's positive, it's going to be here and here.
Yes.
If it's negative, it's here and here. So we're going to fill in now with this chart. And we use a t-table to fill in the rest of it. So I'm going to be over here. You'll notice that I want values from a negative 3 on. Because that's this area right here. Do you see that? So let's put a negative 3 on. And you can use your graphing calculator to help you. Okay? So if I put in a negative 3, I have a negative 3 over a negative 3 plus 2, which is a negative 1. So I'm getting a positive 3. Do you agree?
Yes.
Okay, so
Yeah.
is that right?
Yes.
Okay, so I was wrong. It's here and here, isn't it?
Yeah.
Okay, all right. I'm guessing it's wrong, and it should have been. I got those flipped around. I'm not sure why. Okay, so let's go a negative 4. So I have a negative 4 over a negative 4 plus 2, which is a negative 2, and I'm getting 2. So a negative 4, 2. So a negative 4, 2. Now, if I put in a negative 5, I'm getting a -5 over a -3, which is a positive 1 2/3, correct? And you can see it's going down, right? So 1 2/3 is like this. So what happens is it looks like this. Do you agree? Yes.
So like on the last lesson when we did the graphing like this, you said it was like opposite, like
Yes.
how, is that
It's
opposite
usually,
or is?
yes, it's usually here and here or here and here. Not all the time. You can see on that one, those some examples, sometimes they're both up here. And that's why we have to check them with the t-table.
But I thought that was only if there was like a negative in front of it.
Well, that was quadratic rational equations.
Okay.
Okay, not these. These are a little different.
Okay.
They play the game a little differently. Okay? All right, so now we're going to choose a -1, right? We can't choose a -2. We're going to choose a -1. So if I put a, what's that?
Yeah.
So if I put a -1 in, I get a -1 over 2. Is that right? No.
No, over
Negative
one.
over, what's that?
Over 1.
-1 over 1.
That's right. -1 over it, which is a -1. My bad. Okay, so -1, -1, so it's right here. Nope, it's right here. We put 0 in, we get 0 over this, so it's 0.
0, yeah.
And this is called a 0 of the function. Why?
Oh, no.
Because it's where it touches the x-axis.
Because it's where it touches the x-axis. It's a 0 of the function. So we could have said all of these. This one was 0. This one didn't have one. This one we set it to 0. You see what I'm saying? So if we set the numerator 0, we got it. Okay, so I'm assuming that this one's doing this. Correct?
Yes.
All right. Just and the book doesn't talk about domain and range, but I don't think, maybe it does. Let's talk about domain and range. The domain is to here.
Yes.
Yes.
Negative infinity
Negative
to
infinity
negative
to
two.
negative.
All right, so the domain is, I don't know, can you read that?
Yeah.
The domain is from a negative infinity to
2, negative
a
2.
-2, and then union a -2 to infinity. Do you understand that?
Oh,
Hey, do you understand that?
Yeah.
Okay, so the range comes down, it goes from a negative infinity,
To
right,
the positive 1.
to this right here, and it stops, which is 1. And then it unions 1 to infinity. So keep that in mind as we do domain and range. Question? Nope? Josie, you good?
Yeah.
Okay. Joey?
Yeah.
Now, am I opposed to you plugging this into your calculator? No, not one bit. Even on the test, you can plug it in. I don't care. What I'm going to ask you though is, you know where the asymptotes are, you know where the zeros are, you can find all of those things. That's what I'm going to be concerned about. And I may say, show a t-table. So you may have to show a t-table. But as far as using your calculator, that's fine.
I don't even know how to plug in on my calculator.
Okay, good.
It's easier so I can see the word.
All right.
I'd mess my calculator up.
Okay, so you know this situation right here where the degree of the numerator is greater than the degree of the denominator, and I said there was no horizontal?
Mm-hmm.
It's possible though there's a
Okay.
slant. Okay, a slant. Am I on video?
Barely.
Would you move it, please? We
Yeah.
might have to go back and forth. Okay, a slant asymptote is the toughest. Okay, how do we know when we have the slant of asymptote? Is when the degree of a of x is 1 more than the degree of b of x. So, you know, right here I said there was a slant asymptote. You got it? Because this degree is 2 and this degree is 1. So if any times it's 1 greater, okay, let's take a look at this example right here. And this is hardcore problem, and I want to show it to you because this would be an extreme one. Okay. First of all, This one has a vertical asymptote. The denominator set it equal to 0. The cubed root of 1 is 1. The cubed root of 1 is 1. Right? We took the cube in. So x equals 1 is a vertical, is a, vertical asymptote. So, right here, guys, is a vertical asymptote is right here. Nope,
That's good.
that's negative 1. Right here. Got it? Okay. We good? Now, here's the bad part. The slant asymptote is the numerator divided by the denominator. And we can't factor them, we have to use long division. That's what I'm saying. So, when I use long division, in the box is all of this.
Oh, jeez.
I don't.
And we don't have an x squared term, so we put in an x squared term. We don't have an x term or a constant. Right?
Right. Yeah.
So that's what it looks like. We're gonna do long division. Okay, outside is this. And we don't have an x squared term, so we put one in, we don't have an x term. So it looks like that. You see how I said this is an extreme case? Okay, now because of time, I actually did it so that I wouldn't mess up, because it's very easy to mess up here. But x to the third goes into x to the fourth,
One
1x times.
X.
And I take it times all of it, so x to the fourth plus 0x to the third plus x squared, that's 1, plus a negative x. I'll let you look at it. What I did is I took this x, and I took it times each one of these, so x to the fourth, 1 plus 0, 1 times 0 is 0, so 0x cubed. 1 times 1 is 1, so 1x squared, and then negative 1 times x is a negative x. And I subtract, remember that?
Yeah.
And when I subtract, remember, I go through and I add the negative of all of them. So plus a negative, 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 and this one actually becomes a positive. So this is 0. This is 3x cubed. This is negative x squared, and this is 1x. Is that right?
Yeah.
Okay, and then I bring down to 0. Okay, we good? All right, how many times does x to the 4, how many times does x to the third go into 3x cubed?
Three.
Goes in 3, just 3, right?
Oh, yeah.
And so I take it times that, so I get 3x cubed plus 0x squared, I'm taking it times all of them, plus 3x plus a negative 3. Should be looking at my sheet, I'm not even looking at it. I'm gonna mess up, aren't I? And then I'm gonna be in trouble. So now I'm gonna subtract, and make them all the opposite. So plus a negative, a negative, a negative, and a positive. And so I have, this is negative x squared plus a negative 2x
Plus 3.
plus 3. I don't remember this.
Uh-oh.
Oh, this should be 0. Oh goodness, see how I should have watched my thing? This should be 0, shouldn't it? Because there's no 0x. So this one right here should be 0x squared, which means this is 0x squared, right? It means this is 0x squared, right?
Yeah.
And then 3 times this is a 0x, isn't it? 0x. So this is a negative, this is a 1x. Okay. This is why you look at your sheet when you've already done it, Mr. Ellis. So I'm getting This is cancels this, I'm getting x plus 3, right? Does x cubed go into x plus 3?
No.
No. No.
So is that a reminder?
Yeah.
Yeah,
You
okay.
have to put it over.
But this tells us our oblique, asymptote. And our oblique asymptote is right here, x plus 3. So think of it as this, guys, y equals x plus 3. Okay? Got it?
Yep.
And so, thank you. The y-intercept is 3
3.
and then up 1. So it looks like this. Okay? Now, since it's slanted, I have to use a straight edge. Okay? Now, you would use a t-table, and I'm gonna kind of move things along because we gotta get to one more thing. And what happens is you have it following like this.
Can it have a horizontal asymptote too then?
No, because the degree
Oh,
is,
yeah.
the degree of the
Oh.
numerator is greater than the degree of the, okay, are we good?
Yeah.
All right. And you will not have one that complicated.
Yeah.
All right?
Yeah.
The last thing that we're gonna do is on page 495. The top of the page, point discontinuity. Actually, it's on the bottom. It starts on the bottom of page 494. And it says, in some cases, graphs of rational functions may have point discontinuity, which means a hole in the graph. Okay? It's a hole in the graph. Let me show you an example. These are kind of wild. Number 2, f of x equals x squared minus 16 over x minus 4. Okay? How do we know when we have point discontinuity? Well, first of all, you would look at this and you go, well, that's 2 and that's 1, so it has a slant asymptote, wouldn't you? Because it's 1 up. But
Yeah.
you should notice that this is a difference of squares. You see that?
Yeah.
So it's x minus 4 times x plus 4.
Yeah.
And what happens to these?
They cancel.
They cancel.
They
so it's just
cancel.
X plus
However, before you cancel them, you have to remember that you cannot have 4 as a value, right?
Yeah.
If it was a normal one, this would be an asymptote, x equals 4, right?
4. Yes.
But it's not a normal one because they cancel. So keep that in mind. So basically we get, remember f of x is a fancy way to write
Why?
Why?
y. So y equals x plus 4, and that's a line, isn't it?
Yeah.
So this is your answer. It's not a curvy thing, it's a straight line.
Sweet.
All right, so if you'll follow me over here with the camera, it's a straight line. So if I graph y equals x plus 4, watch this, guys. It has a y-intercept of 4, it has a slope of 1, correct?
Yes.
So it looks like this. It's very fun to graph. It's way easier than those other ones, correct? However, it has one point that it cannot be.
Full.
4.
It cannot be 4. X cannot be 4.
Yeah.
So I go 1, 2, 3, 4. This value cannot happen on that graph. So I follow it up until I get to the point that it happens,
You put a break.
and I put a big old hole there. And that tells the reader that doesn't work. That point does not work. Everything else works but that point. You understand it? So it looks like it's one with a slant asymptote, but you can cancel the common factors. Therefore, it has a hole in it.
Will it always be able? You will always be able to cross cancel like that.
If it's factorable, yes.
Okay.
But not, sometimes you'll just have an automatically slant asymptote. This will be larger and you couldn't factor it. Okay?
So you'd have to trial and error.
You would have to do this.
Oh.
So slant asymptotes are not fun. Okay? All right. So your assignment is page, can you put that on the assignment? It's page page 496. Okay? Page 496, 13 through 22. Page 496, 13 through 22. There's not a lot there. I mean, but it's time consuming. And 28 and 29. Okay?
When is this due?
When is this due? Okay, so tomorrow you'll be maths testing,
Yeah.
and then
Thursday
we're
and
all
on Friday.
and
we're
then
gone.
Friday I'll give you a chance to work on it. The problem is I'm not gonna be here Friday,
Yeah.
so you're gonna have to kind of work on it on your own. Okay? But it's due Monday. All right?
Yeah.
All right, let's stop her.